Well, good afternoon. It's great to be here. I feel like I had the hardest job in the whole conference because I have to talk about the oldest technology. So it's the least exciting, but I'm going to try and make it exciting today. As Sue mentioned, EBI is a partnership between 3 different academic institutions, UC Berkeley, Lawrence Berkeley Labs, and the University of Illinois Urbana-Champaign. We're funded solely by BP, which is a very interesting arrangement for academics. Our money comes in through the university system. We're an open, completely peer-reviewed academic endeavor. So I'd be happy to talk with anybody about how that relationship actually works. But it's been very successful so far. We've published more than 200 open peer-reviewed papers in the literature with, I think, a dozen science papers now, to our credit. And it's just been a really incredible opportunity for the academics. These are all regular academic university faculty members, graduate students, postdocs working in the area. Okay, and they get to talk to some people in industry and kind of ground truth what they're doing, and that's really an incredible opportunity. Okay. So, biomass electricity. This is a really interesting area. Most of our research at the EBI is actually around the biofuels question because we feel that that's really the critical area that needs advanced research. Biomass electricity has been around for a long time. We know how to do this. But I think what's interesting about it is that it may have a very important and key role in our energy portfolio. So you may not know that biomass, according to the IEA, is right now the most important source of renewable energy. I thought that was kind of shocking. It's 10% of the total primary energy and 78% of total renewable energy. Okay, so the caveat on this is, of course, that the primary uses are in cooking and heating in the developing world. These are inefficient processes that have high emissions. So this is something that needs to be improved. But they also make a lot of our portfolio. So actually, 38% of our renewable portfolio in the US comes from biomass. And this is bioelectricity and biogas. So that's what I'll be talking about today. The nice thing about this technology is that it is something that's on the ground. It's something we can do today. It's not something, this 20 years out. It can substantially lower our carbon footprint. And I think the most revealing part for me was I just finished a 2-year study with the California Council for Science and Technology, and we looked at California's energy future to 2050, the entire system. Okay, we did 4 things when we did this study. The first thing we did was to implement as much efficiency as possible in the state, and this was a study out of Lawrence Berkeley Labs. The next thing we did was to electrify as much as possible, because there was consensus in the group, and this was 50 scientists from around the state looking in the issue, that electrification isn't generally more efficient. The next thing we did was to try and decarbonize our electricity and our remainder of fuel. And what we found when we did that study were 2 things that relate directly to biomass. First is the importance of biofuels. And so I'll just, kind of follow up with Sue's nice talk about where we think that industry is going, but we could not meet the governor's mandate for greenhouse gas reductions unless we addressed the fuel question. That was just an absolute. We couldn't even get to 60% greenhouse gas reductions without addressing the fuel question. The second thing was in our renewable portfolio development, we discovered that there was a critical role for biomass in stabilizing baseload electricity for intermittent renewables and in peaking, so power balancing. And this was something that's right now served only by the natural gas industry. So this is a critical role for biomass electricity and biogas. Okay, so I wanted to talk just a little bit about feedstocks because I think there's a lot of misinformation about biomass feedstocks. The first is that we actually are in a situation in this country where we have increased biomass growing. Our forest stocks have increased almost 10% over the last 10 years. Why is that? Does anybody have a guess? Sorry. It's because we lost our forest products industry. Okay, we stopped harvesting our biomass. And I think the result of that has been shown in massive wildfires and other types of disasters where we need to be managing our forests better. So I don't actually think that this increase in biomass is necessarily a good thing. We're in the middle of writing a paper right now that actually looks at the rates of forest growth, forest maintenance, and carbon fixation. And what we find is that in an actively managed forest where you are harvesting some portion of the biomass, and let me just be clear what we're harvesting here. Right now we harvest 1% of our total forest biomass, which is less than 60% of the annual growth. So there's opportunities there to actually improve our biomass harvest at an annual growth level that is sustainable, okay, and that meets our goals of having very healthy forests. The second is this increase in agricultural biomass per acre has been completely underestimated. Farming techniques have changed. I don't know how else to say it. We've gotten better at planting more plants per acre, and we do it with a lot lower intensity for inputs. So there's environmental awareness that's cueing this. It still has a long way to go. Agriculture is the biggest emitter of greenhouse gases right now with fertilizer use, and we'd like to see this change. This is not the kind of feedstock that we're talking about for bioenergy. So Sue mentioned we've been looking at the EBI at a number of different feedstocks that would be advanced feedstocks that would not compete with food at all, completely different acres. We're looking at energy grasses, things that are perennial, they're not tilled, they're planted once, they're harvested yearly without fertilizer, completely input-free, rain-fed. Okay, no irrigation for perennial grasses. We're also looking in arid regions. This came up in the California study. We want to have plants that can grow with very little rainfall, like agave. These are planted now on a commercial scale for tequila production and for sisal production in Madagascar, huge plantations. And these plants naturally go through a growth cycle where they grow to a very huge, this is, again, a real-sized person. In 5 years, this is the biomass growth. And at the end of that cycle, the plant dies. So that's biomass that can be harvested as part of its natural growth cycle. The other opportunity in the north is short rotation plants, short rotation woody plants, coppice species, again, that can be harvested without being replanted and that can regrow at a very high growth rate. So what we see is a change in what we have selected for typically in the past, which is fruit yield. We select for grain, right? We select for what tastes good and what looks pretty. Our whole horticultural industry is grown up on that. And those are not the traits that we want for this industry. What we want is energy production per acre. We want low inputs. We want something that's going to be environmentally sustainable. It's going to grow on a fast scale because we want to do this, capture our annual carbon on a yearly scale. And we want to do this with a lot of knowledge and forethought about what are the right plants for the region. Right now, our agricultural industry is entirely the opposite. It's about where can I grow corn? Can I grow corn in the desert? Some of the highest production of corn is actually in Arizona. So does that make sense? I don't think so. Okay, so when we walked through this exercise for California's energy future, we looked at all of these different types of feedstocks. Woody energy crops, woody residues, herbaceous energy crops, these are the grasses, crop residues of all sorts. So this is orchard trimmings, nut hulls, you name it, any kind of straw. We looked at municipal solid waste, and I have to be clear here that we're talking about the organic portion of municipal solid waste, not the recyclable portion. We don't want to interfere with recycling programs, and we're not interested in burning plastics. We looked at animal waste and municipal wastewater as sources. When this issue of trying to supply baseload electricity and natural gas substitutes for the renewable portfolio came up, we shifted our emphasis from looking at biofuel production, which had been the focus of that portion of the study, to looking at an integrated system that would look at biogas and electricity and the synergies between these different activities. So actually, when you put in any kind of biofuel plant, you're going to have residual biomass that's left over that you can burn. This happens in Brazil. Brazil exports a huge amount of electricity to the grid right now. So that would be a direct cogeneration of things that are left over. In the cellulosic process, this would be lignin that is not biologically convertible to fuel with present technology. You also have wastewater streams. If you're doing fermentation, you have giant vats of stillage. These are yeast cultures, basically, that you need to dispose of. This happens in the beer and wine industry now. And so this is a huge problem. trying to get rid of this waste, and that can be turned instead into an opportunity. You can take that and treat it through anaerobic digestion to make biogas. You can use the water on the fields and reclaim nutrients from that process. So you can actually end up generating quite a bit amount of electricity and biofuel at the same time. And the nice thing about that is that then you've then co-located these activities where you're bringing the biomass in. You don't have a separate supply issues for biomass. Okay, so turning to the heat and power issue, this is probably old hat for all of you. I won't spend a lot of time on it, but the three main technologies that I'm going to talk about are basic combustion, where you're just getting heat and using that to make steam electricity. This would be your conventional heat and power pathway. Biological gasification, or the anaerobic digestion to make biogas. You can also make a little bit of hydrogen in that process, but it's pretty minimal. And then, of course, the other technologies, which would be thermal gasification, which is a much more efficient way of accessing the energy in the biomass. And that you can use to directly create steam and electricity and heat, or you can use the gases that you create to do synthesis for other molecules. So the status of these technologies, most of them are down here. They're in the mature technology end of the scale. So that means that we have renewable technologies today that can meet these unmet needs, which is the good news. The better news is that we have more efficient technologies coming online. So gasification right now is sort of down in this end of the curve. It needs a little bit of work to make a high-quality gas that we want to do lots of things with. If we just want to harvest the energy and make electricity, we can do that right now. But if we want to use it for chemical synthesis, we have to do a little bit of cleanup. And co-firing with coal is another option where I personally don't like talking about this one very much because I think it's a bad precedent. And we're talking about renewables here. We want to get away from fossil fuels. The nice part about co-firing with coal is you can reduce the greenhouse footprint. And so it can be a bridging technology in areas that maybe can't afford to do complete switching to renewables. But right now there's a very low tolerance for biomass inclusion in these facilities, so it's about 15%. And as you see, the high co-firing rate is way over here. And I personally hope that the renewable technologies that we're talking about in these 2 days replace that option. So again, each one of these options has positives and negatives. Efficiency is low in direct combustion, but it is the proven low-risk option. So it is the thing that you're going to see the most in the next few years. If you do it with combining and capturing the heat, that can actually be quite efficient. And so I'll give some examples of companies that are doing that. Gasification is much higher efficiency, but it's a much higher cost. And again, the co-firing option is there. This turned out to be a big part of America's Energy Future Study by the Academy. So it's something that we have to consider as being in the mix and in the political dialogue. Okay, so I wanted to give a few examples of installations that have gone in. This is a 70 megawatt plant in Florida that uses waste biomass from sugarcane. So this is very similar to what you see in Brazil, where you're making sugar, extracting that from the cane plants, and then you have this big pile of refuse, which is basically the canes that have been crushed and all the sugar extracted. And right now, that just sits in a pile and rots. If you wanted to use it for electricity, it can be quite efficient. This is another example of, this is the biggest biomass plant in France, and it's another example of how biomass electricity can be synergistic with other uses. So here, we could use that electricity to power the sugarcane plant or a biofuels plant. Here, it's being combined with a paper company. So the paper company brings in wood, they extract the fiber, they have lots of residual biomass in terms of bark and sawdust. They feed it next door to this plant. They also feed them their high temperature steam that they can't use. And this plant converts all of that to electricity that they feed back to the paper mill along with low temperature steam for use in their process. So it's a very synergistic type of arrangement.